Welcome. Today we're diving into the fascinating world of inferential statistics. If you've ever wondered how researchers make predictions or draw conclusions about a large group based on a small sample, you're in the right place. Inferential statistics is the branch of statistics that helps us move beyond mere data description. Instead of just summarizing what we see, it empowers us to make educated guesses and test hypotheses about population. Throughout this video, we'll break down the core concepts, walk through practical examples, and help you understand why inferential statistics is so essential in research, business, and everyday decision-making. Before we go deeper, let's clarify the difference between descriptive and inferential statistics. Descriptive statistics is all about summarizing and organizing data, think averages, percentages, and charts. Inferential statistics, on the other hand, takes things further. It allows us to make predictions or inferences about a population based on a sample. For example, if you survey 100 people about their favorite ice cream flavor, inferential statistics helps you estimate what the entire city might prefer. This distinction is crucial for understanding the power and limitations of statistical analysis. Statistics, the term population, refers to the entire group that you want to draw conclusions about. This could be all the residents of a city, every product made in a factory, or every student in a school. Populations can be large or small, but the key is that they represent the full set of items or people you're interested in. Since it's often impossible or impractical to collect data from every member of a population, we rely on samples to make inferences. Sample is a smaller group selected from the population. It's like taking a slice of cake to judge the flavor of the whole dessert. The goal is to choose a sample that accurately represents the population, so the conclusions we draw are valid. Sampling is a practical solution when studying the entire population isn't feasible. The methods used to select samples are critical, as a poorly chosen sample can lead to misleading results. Random sampling is one of the most important techniques in inferential statistics. It means every member of the population has an equal chance of being selected for the sample. This approach helps ensure that the sample is unbiased and truly represents the population. For example, if you're surveying students in a school, random sampling would mean every student has the same chance of being picked, regardless of grade or background. Sampling is at the heart of inferential statistics. By carefully selecting a representative sample, we can make reliable predictions about the entire population. This saves time, money, and effort. However, if the sample is not representative, our conclusions may be flawed. That's why statisticians pay close attention to how samples are chosen and strive to minimize sampling errors. There are several ways to select a sample. Common methods include simple random sampling, stratified sampling, and cluster sampling. Each method has its strengths and weaknesses. Simple random sampling is straightforward but may not capture important subgroups. Stratified sampling divides the population into groups and samples from each, ensuring representation. Cluster sampling selects entire groups at random, which can be more practical in large populations. No sample is perfect. Sampling error refers to the natural differences that arise between a sample and the population it represents. Even with random sampling, there will always be some variation. The goal is to minimize this error as much as possible. Understanding sampling error helps us interpret results more accurately and avoid overconfidence in our conclusions. Inferential statistics, a parameter is a value that describes a characteristic of a population, like the average height of all adults in a country. A statistic, on the other hand, is a value calculated from a sample, such as the average height of 100 randomly selected adults. We use statistics to estimate parameters since we rarely have access to the entire population. The main goal of inferential statistics is to make inferences about a population based on sample data. This involves using probability theory to estimate how likely it is that our sample results reflect the true population. By understanding the relationship between samples and populations, we can make informed decisions and predictions, even with limited information. Probability is the backbone of inferential statistics. It helps us quantify uncertainty and assess the likelihood of different outcomes. When we say there's a 95% chance that a result falls within a certain range, we're using probability to express our confidence. This is crucial for interpreting statistical results and making sound conclusions. Confidence interval gives us a range of values within which we expect the true population parameter to fall. For example, if we estimate the average test score to be 75 with a 95% confidence interval of 70 to 80, we're saying we're 95% confident the true average lies in that range. Confidence intervals help us understand the precision of our estimates. Hypothesis testing is a core process in inferential statistics. It's a structured way to test assumptions or claims about a population. We start with a null hypothesis, which is a statement of no effect or difference, and an alternative hypothesis, which is what we hope to support. By analyzing sample data, we determine whether there's enough evidence to reject the null hypothesis. Significance level, often denoted as alpha alpha, is the threshold we set for deciding whether a result is statistically significant. Commonly, this is set at 0.05, meaning we're willing to accept a 5% chance of making a wrong conclusion. If the probability of our result occurring by chance is less than alpha, we reject the null hypothesis. P-value tells us how likely it is to observe our sample results, or more extreme if the null hypothesis is true. A small p-value, usually less than 0.05, suggests that our results are unlikely to have occurred by chance, leading us to reject the null hypothesis. P-values are a key tool in hypothesis testing. In hypothesis testing, two types of errors can occur, type I and type II. A type I error happens when we wrongly reject a true null hypothesis, while a type II error occurs when we fail to reject a false null hypothesis. Understanding these errors helps us interpret results responsibly and design better studies. The power of a statistical test is the probability that it correctly rejects a false null hypothesis. High power means we're more likely to detect a real effect when it exists. Factors affecting power include sample size, effect size, and significance level. Researchers aim for high power to ensure their studies are effective. There are several common inferential statistical tests, including t-tests, chi-square tests, and ANOVA. Each test is designed for specific types of data and research questions. For example, t-tests compare means between two groups, while ANOVA compares means across multiple groups. Choosing the right test is essential for valid results. Every statistical test comes with assumptions such as normality, independence, and equal variances. Violating these assumptions can lead to incorrect conclusions. It's important to check whether your data meet the requirements before running a test. If not, alternative methods or adjustments may be necessary. Once you've run a statistical test, interpreting the results is key. Look at the p-value, confidence intervals, and effect sizes. Consider the practical significance, not just statistical significance. Results should be communicated clearly with an understanding of their limitations and the context of the study. Let's consider a real-world example. Suppose researchers want to know if a new drug lowers blood pressure. They test it on a sample of patients and use inferential statistics to determine if the observed reduction is likely to occur in the general population. By analyzing the data, they can make informed recommendations for wider use. In business, inferential statistics is used to predict consumer preferences. For instance, a company surveys a sample of customers about a new product. The results help estimate how the entire market might respond, guiding marketing strategies and product development. This approach saves resources and reduces risk. While powerful, inferential statistics has limitations. Results depend on the quality of the sample and the appropriateness of the methods used. Bias, sampling errors, and incorrect assumptions can all affect the validity of conclusions. It's important to interpret findings cautiously and consider alternative explanations. Ethical considerations are vital in statistical inference. Researchers must ensure transparency, avoid manipulating data, and report results honestly. Misuse of statistics can lead to false claims and harm. Upholding ethical standards builds trust and credibility in research findings. Modern statistical analysis often relies on software like SPSS, R, or Python. These tools make it easier to perform complex calculations, visualize data, and run tests. However, understanding the underlying concepts remains essential for interpreting results correctly and avoiding mistakes. Graphs and charts are powerful tools for presenting inferential statistics. Visualizations help communicate findings clearly and make complex results more accessible. Common visuals include bar charts, histograms, and confidence interval plots. Effective visuals support better understanding and decision-making. Clear reporting of statistical findings is crucial. Reports should include details about the sample, methods, results, and limitations. Transparency allows others to evaluate the validity of the conclusions and replicate the study if needed. Good reporting practices strengthen the impact of research. Replication is the process of repeating a study to see if the results hold up. Reliable findings should be reproducible by other researchers using similar methods. Replication builds confidence in statistical inferences and helps identify errors or biases in original studies. With the rise of big data, inferential statistics has become even more important. Large datasets offer new opportunities for discovery, but also present challenges in sampling, analysis, and interpretation. Statisticians must adapt traditional methods to handle the scale and complexity of modern data. Machine learning often relies on inferential statistics to make predictions and classify data. Algorithms use sample data to learn patterns and make inferences about new, unseen data. Understanding statistical inference helps improve the accuracy and reliability of machine learning models. There are several misconceptions about inferential statistics. For example, some people think a statistically significant result always means practical importance, or that a p-value tells us the probability a hypothesis is true. Clarifying these misunderstandings is key to proper interpretation and application. Statistical literacy is the ability to understand and use statistics effectively. Improving this skill helps people make better decisions, evaluate claims, and avoid being misled by faulty data. Education and practice are key to building confidence in interpreting statistical information. Inferential statistics plays a major role in policymaking. Governments and organizations use statistical inferences to guide decisions on health, education, and economics. Reliable data analysis leads to better policies and improved outcomes for communities. Collecting high-quality data is a challenge in any statistical analysis. Issues like non-response, measurement errors, and biased sampling can affect the accuracy of inferences. Careful planning and rigorous methods help minimize these challenges and improve the reliability of results. As technology advances, inferential statistics continues to evolve. New methods, software, and data sources are expanding what's possible. Statisticians are developing innovative approaches to handle complex data and answer challenging questions, ensuring that inferential statistics remains a vital tool for discovery. Let's recap the key concepts we've covered. Inferential statistics allows us to make predictions about populations using samples. It relies on probability, hypothesis testing, and careful sampling methods. Understanding its strengths and limitations is essential for accurate data analysis and interpretation. If you're new to inferential statistics, start by mastering the basics. Understand the difference between populations and samples, learn about common tests, and practice interpreting results. Use real-world examples to build your skills, and don't hesitate to consult resources or seek guidance when needed. There are many resources available for learning more about inferential statistics. Online courses, textbooks, and tutorials can help deepen your understanding. Joining study groups or online forums is also a great way to discuss concepts and solve problems together. Be aware of common pitfalls in inferential statistics, such as overgeneralizing from small samples, ignoring assumptions, or misinterpreting p-values. Always check your data, understand the methods you use, and interpret results within the proper context to avoid mistakes. Working with professional statisticians can greatly improve the quality of your research. They bring expertise in study design, data analysis, and interpretation. Collaboration ensures that studies are well designed, results are valid, and conclusions are robust. Effective communication is key to sharing statistical findings. Use clear language, visuals, and summaries to make results accessible to a broad audience. Tailoring your message to your audience helps ensure your insights have the greatest impact. In education, inferential statistics helps evaluate teaching methods and student performance. Researchers might compare test scores from different classrooms to see if a new curriculum is effective. By analyzing sample data, they can make recommendations for broader implementation. Environmental scientists use inferential statistics to study pollution, climate change, and wildlife populations. By collecting samples from different locations, they can estimate broader environmental trends and inform policy decisions. This approach is vital for protecting natural resources. In sports, inferential statistics is used to evaluate player performance and predict outcomes. Teams analyze sample data from games to make decisions about training, strategy, and recruitment. This data-driven approach gives teams a competitive edge and improves performance. Inferential statistics is a powerful tool for making sense of data and drawing conclusions about the world. By understanding its principles and applying them carefully, you can unlock valuable insights and make better decisions. Whether in science, business, or everyday life, inferential statistics helps turn data into knowledge.